Continuation marks are a building block for various forms of dynamic scope. Now, of course, you don't usually want dynamic scope, but it's good for certain things, such as the current directory for resolving relative paths. In contrast to something like a file creation mode or binary versus text, it would be very painful to pass the current directory all the way through all parts of your program that need it. Now, I'm not advocating for a process global state. Indeed, I might want to have multiple threads in my process, each working in a different directory. I don't even want thread local state, because that's painful if I want to change it temporarily within a thread and have to deal with the possibility of exceptions or other kinds of escapes. I might have coroutines or generators, where I run a generator-specific current directory. I may even have something like futures in my language, where a computation is run speculatively in parallel on an unspecified thread and shifted among threads. Instead of state, what I want is, just as the picture suggests, to attach the current directory to the computation. The generic name for these kinds of computations is a continuation, and that's why we call the setting attached to it a continuation mark. In Racket, a programmer adjusts the current directory by setting a dynamic variable, also known as a parameter. The parameterized form adjusts the dynamic variable while it's evaluating its body, in this case shuffle files. During that evaluation, the value of a parameter is available by calling the parameter like a function. But parameters and parameterize, these are not the primitives in Racket. Instead, parameters are implemented in terms of with continuation mark, which I'll abbreviate on the slides with mark. Mark takes a key like current directory and maps it to a value like home Alice, and to look up the value for that key, the current mark primitive looks in the current continuation and gets the most recent value for that key. There's also a more general primitive, current marks, that gets all the values for a given key in the continuation in order, and we could get all the marks and just use the first one for parameters. Parameters are just one language construct implemented with continuation marks. Here are a list of some others, some of which are described by papers, for constructs in Racket. For about half of these, we only need current mark, the most recent mark on a continuation, but for the others that we need current marks to reflect more generally on a continuation. You may notice also that the first paper here is almost 2 decades old, so continuation marks have been around for a while in Racket. They've proven to be an important part of Racket's language building toolbox, right alongside closures and tail calls and first-class continuations. So why are we revisiting this after 2 decades? It's because we've been porting Racket to run on top of Chez. Racket is state-of-the-art in its language building expressiveness, with delimited continuations, continuation marks, and so on. Chez, meanwhile, provides state-of-the-art performance, whether for straight-line code, function calls, or first-class continuations. But it just provides callcc. Now, Chez-Scheme's efficient callcc implementation is a great basis for implementing most of Racket's delimited continuations API. And it can also implement continuation marks. The performance there is just okay. And since continuation marks are such an important building block in Racket, it's worth spending some effort on the optimizer to specialize it further. When we do that, performance on individual continuation mark operations can improve by up to a factor of 20. That translates into an improvement of up to 3 or 4 for derived concepts like contracts in Racket. And for whole realistic applications, that translates into a performance improvement of 10 to 25%. For the rest of this talk, I'll provide a refresher on the semantics of continuations and marks, a refresher on how to implement continuations in a hybrid Stack-Heap model, and then finally explain how we take advantage of that model to get an efficient implementation of continuation marks. Let's start by converting expressions into picture form. To evaluate this expression, we first have to subtract 7 minus 3. Once we get a value from that, we can deliver it as the first argument multiplied with 2, and once we get a value from that, we deliver it as a second argument added with 1. The picture on the right provides the same information as the picture on the left, but the picture on the right more directly suggests a continuation. There's the current expression that we're evaluating, 7 minus 3 is 4. Once we get a value 4, we deliver it to the rest of the continuation. Now we have a new expression to evaluate, deliver that result to the rest of the continuation, and so on. For most of the talk, instead of arithmetic, I'll use in traditional lambda calculus style functions and applications, but it's going to be the same kind of picture and the same idea. Here, we reduce that function call to v3 and just get the value v3, which can be delivered to the rest of the continuation. But let's back up and suppose that the body of that function is more complicated. Let's suppose that when we substitute in v3 for x, we get some other expression e2, which is not yet a value. Our pictures should properly reflect tail evaluation, which is that we continue to use the same continuation frame to evaluate the body of that function e2 as we did for the call. That's true for function calls, for tail calls, and more generally tail evaluation for other forms that have tail positions. When we use callCC in Scheme, callCC captures the current continuation and it delivers it as an argument to a given function. So the continuation is going to go in as k here for k applied to v3. That means when we capture the continuation and substitute it in, we'll have this continuation applied to v3. The meaning of continuation application is that we throw away the current continuation, replace it with the applied continuation, and deliver the argument value to that continuations. So our pictures can express things like continuations and tail calls and continuation capture. Let's now introduce continuation marks. Here's that example similar to earlier, where we map current directory to home Alice, but let's make it generic again, some arbitrary key v7 mapped to a value v10. The semantics of withMark is that we take the key and value and put them together as a binding and a little badge on the current continuation frame. So that's why it's a continuation mark. It's sitting right there on the frame. And then withMark proceeds by evaluating its body in tail position. In this case, the tail expression is another withMark, so we map v9 to v11, again in the continuation frame. Since v7 and v9 are different keys, they both are in the mark for this continuation frame. But if we back up, and if that were mapping v7 to v13, then the meaning of withMark is that we would replace the mapping for v7 in the current continuation frame. And this replacement makes continuation mark update in sync with tail evaluation of expressions. If we have withMark inside of withMark but not in tail position, so first we map v7 to v10, but now we have an application form, v0 applied to an argument, we have to start evaluating that argument in a new continuation frame. Now withMark v711 gets added to the new continuation frame. It does not overwrite the other one, and if we reflect on this full continuation, we can see a history of values for v7. As the computation proceeds, we might reflect on that history using current marks. It takes a key like v7, looks in the continuation to find all the uses of that key, and produces a list that has all the values associated with that key. If the current marks frame here had its own continuation mark mapping v7 to v12, that would make v12 included in the list as well. Continuation marks work with callCC in the obvious way. Whenever we capture a continuation, any marks associated with that continuation's frame stick with the frames, whether it's captured or when the continuation is applied later. When we capture a continuation, we don't want to actually copy the rest of the continuation like the picture suggests. Instead, we just want to grab a reference to the current continuation and deliver that to the argument of the callCC as a constant time operation. We have to be careful to implement this in the right way, though, because after we capture a continuation and computation continues with that continuation, we want to make sure that the capture continuation does not change, which these pictures suggest it might if evaluation proceeds and changes a mark on the current frame. To address this issue, let's refine our picture to get closer to the implementation. Instead of attaching marks directly to continuation frames, we'll put them in a separate list referenced by a marks global register. That way, whenever we change the marks on the current frame, instead of changing the frame, we'll just update the marks register. And instead of mutating an existing badge whenever we add marks in a frame, we'll just allocate a fresh badge record to put into the marks list. Now, the marks register refers to the marks for the current frame. Meanwhile, each frame has a reference to the rest of the continuation, as well as the marks that apply for the rest of the continuation. Then again, a drawback of this representation is that every frame has to refer to marks, even though marks can change less frequently than continuations, and in fact in practice are much less frequently changed than continuation records. To address this, we can introduce special continuation frames that are just there to reset the marks on a return. That way, most frames just refer to the rest of the continuation, while these special frames also refer to a marks list to restore. This is closer to the actual implementation, but to get even closer, we need to switch from heap-allocated frames to stack-allocated frames, because for performance reasons, that's how we actually implement things. To do that, I need to give you a refresher on implementing first-class continuations with stack-based continuation frames. With a stack, callCC will need to copy part of the stack to capture a continuation. But instead of copying eagerly, we'll copy lazily with a kind of copy-on-write strategy. CallCC will just split the stack into its old part and the new part where it's still working, declare its own frame to be the beginning of the new part, and capture a reference to the old stack as the continuation. Later, when that continuation is applied, then it gets copied. At the same time, we need to take care of the possibility that callcc returns instead of having its continuation applied, so the return address is also set up to copy in the old stack. If the continuation is applied, then that old stack is copied into the current stack, replacing whatever was there, and the argument to the continuation is delivered to that stack. If there are no other references to the continuation, the old stack can go away by garbage collection, and now we're back to the simple case, as if we had just returned v3 in the first place. In the case of capturing a continuation but not using it, the same sort of thing happens. Return treats the old stack as a continuation that gets copied in, the return value is delivered there, the old stack can be GC'd if there are no other references to the continuation. While this copying may look expensive, it performs well with suitably sized stack segments. Now in this picture we have two red arrows to the old stack, both representing the old continuation, but they can't be actually the same address because they're different kinds of values. The arrow on the left is a continuation that looks like a function, the one on the right is a return address. So let's refine our picture again to show in each continuation frame that there's a return address at the beginning of the frame. Let's also, instead of writing stack base at the bottom, have an actual stack base register that records the current stack that we're working in, and a frame register that points to the current stack frame. When callcc captures the current continuation, it creates a new continuation record and remembers the current stack by copying the stack base value. It then adjusts the stack base register to point to the current continuation frame, effectively splitting the stack. We also record the current return address and the pointer to the shallowest frame and the captured continuation. Now we have a continuation record that we can supply as a value. Applied as a procedure later, it will invoke that continuation. Meanwhile, to handle the possibility of direct return, we remember this continuation record in an extract register, and we set the return address on the current frame to underflow. Underflow as a return address will cause next stack to be applied as a continuation, thus having the same effect as directly applying the continuation. So, stepping back for a moment, we have a set of stack segments, each created by callcc, that are chained together in the heap through the next stack list. So that's the Stack-Heap hybrid that gives us the best of both worlds. If we're in this state, we're about to apply the continuation, then the continuation record identifies that old stack segment to copy in. So that gets copied in, replacing what was there. The argument to the continuation gets delivered as the result into that first frame, and evaluation proceeds. Meanwhile, the next stack pointer is adjusted to point past the continuation that we just applied. If there are no other references to that continuation, then it can be garbage collected, and once again we get back to the simple state as if we had just returned v3 directly. Finally, we're ready to implement continuation marks. Evaluation of a with mark form, of course, creates a new badge, mapping the key to the value, and puts it into the marks list. But it also reifies the current continuation in the same way as callcc. That way we have a continuation record that gives us a place to store the old marks. And it turns out this is going to cause the marks that with mark just pushed onto marks to be popped as we return from the current frame. Meanwhile, with mark continues evaluation with the body form. In this case, the body expression is another with mark form. It was in tail position with respect to the previous with mark, so we should not push further marks, we should instead replace. And the way we know to do that is the return address is already set to underflow. So with mark sees that the return address is set to underflow. It doesn't try to reify the continuation again. Instead, it just replaces the current marks record with a fresh one, mapping the key to the new value. Once again, we continue evaluation of the body expression E3. Eventually, it produces some value V3. And now as we return, it's the same as returning to a continuation. That is, we copy the old stack in place, we set the next stack pointer to the next record in the continuation, and now we also update the marks register to point to the marks that are recorded in the continuation. At this point, the old continuation and marks are inaccessible, so they can be GC'd, and we get back to the right place with a simple stack and no marks on our continuation frame. So it can be as simple as that. With mark reifies the continuation, then pushes onto the mark stack, and just returning to the continuation has the effect of popping the mark stack, getting rid of the marks that should go away as the current frame goes away. There are several opportunities for optimization for with mark. For example, this continuation copy that we did when returning, that wasn't really necessary. And that's because when with mark reified the continuation, that continuation is only referenced from the next stack pointer. That is, it's a one-shot continuation. We don't need to copy when we resume that continuation because no one else is going to need that copy. Our implementation takes advantage of this possibility in an opportunistic way. That is, as long as the current continuation has a one-shot flag on it, and as long as the continuation that we want to resume, its stack resides right below the current stack frame, then in that case, instead of making a copy, the stack base pointer is moved back to its old location, and the next stack and marks just go back to what they were. It's opportunistic because a capture through call CC might happen after with continuation marks, in which case that one-shot flag is removed. Or another possibility is that there's a garbage collection between the time that the continuation was reified and that we returned, and in that case the stacks may not be next to each other. However, in the common case of using withMark in a program without callcc, then this is a frequent opportunity that the implementation can exploit. Another optimization builds on something that every compiler will do, which is that when we have a non-tail expression that is a simple primitive operation like addition, that primitive operation will get inlined instead of creating a new frame. It's only when we have a function call in general that a non-tail expression has to create a new frame. So along those lines, when we have withMark in a non-tail position, then the withMark can just directly push onto the mark stack, start evaluating its body. If that body turns out to be something simple, like again a primitive operation that is going to be inlined, it can perform that operation, get a value back, and then perform an explicit pop as it returns to the rest of the frame. On the other hand, if the expression inside of a non-tail withMark turns out to be a function call, then that function call really does need a continuation frame. In that case, withMark should have belonged to that other frame. So for those calls, we reify the continuation as we make the function call, just the same as if withMark had been put into the new frame. And a compiler can statically detect which function calls need to be treated in this special way. Overall, performance improvements come from a combination of these optimizations plus the representation of marks as part of continuations. And that is how we get all of the expressiveness of Racket's language building blocks with all of the performance that Chez scheme provides.